Well, now we're going to prove L'Hopital's rule. So let's begin again by stating L'Hopital's theorem or L'Hopital's rule. F and G are continuous on a closed bounded interval and differentiable on the open interval from A to B. X naught is some number in between A and B inclusive in a closed interval AB. If the derivative of X is never zero, the derivative of G is never zero for all X in A to B. And part two, that F of X naught and G of X naught are both equal to zero. And then the third one says, if the limit of the derivatives exists, the limit as X goes to X naught of the derivative of F over the derivative of G exists, then we have found the limit of F of G, F over G of X. Well, the proof is going to use sequences. And we're going to start off by having a sequence xn that converges to x naught, where xn is taken from any numbers in AB, the interval AB, excluding x naught. So xn is going to converge to x naught. By the Cauchy mean value theorem, there is a sequence Cn such that these two things hold. Well, the first one is we're just choosing Cn to be strictly in between xn and x naught. So either, depending on whether xn is to the right of x naught or to the left of it, it's either going to be this case or this case. I could have said just make Cn strictly in between x naught and xn for all in the natural numbers. So basically, if that's x naught, and here's our interval, if this happens to be x1, well, C1 is going to be somewhere in here, like right there, C1. If x2 happens to be here, well, C2 is going to be somewhere in here. That should be easy to see that if the xn's are converging to x naught, and the cn's are always closer to x naught than the xn's, by the squeeze theorem for sequences, we know that, I can write that here. We can say, so Cn also converges to x naught. By the way we've defined Cn. Well, also, and here's where we use the Cauchy mean value theorem, since Cn is in between x naught and xn, this is the formula for the Cauchy mean value theorem, only we're applying it for every n in the natural numbers. So this, basically we're saying the Cn exists in that interval because of the Cauchy mean value theorem. Well, the next thing we're going to look at is we're going to note or notice that xn not equal to x naught for all n, and g prime of x never equaling 0 on the entire interval AB means that g is a one-to-one function. And that is by Theorem 4.9, Part 1. And that also implies the fact that g is one-to-one means that g of xn is not equal to g of x0 for all n. That just follows from g being one-to-one. Oops, sorry. I just left one little thing out. G of x0 is 0. So g of xn is not equal to 0, because it's not equal to g of x1, g of x naught, which is 0. All right, well, something else we know is since g of x naught and f of x naught are both 0, that implies that if I want to take something that looks like f over g, I can say that, which is a term in a sequence. It's the nth term in the sequence f over g. I should say f over g of xn. Well, that's equal to itself, of course. And I'm going to add something to the numerator and the denominator, which in our case is all I'm doing is subtracting and adding 0. F of x naught and g of x naught are both 0, so I've made no change there. But by the Cauchy mean value theorem, this thing, which should look very familiar, is equal to f prime of Cn over g prime of Cn. That's by the Cauchy mean value theorem. And basically, that comes from this formula right here. If we were to solve this for divide both sides by g prime of c over n, we get this. Divide both sides by this, we get exactly this. So I could have said by 2 above, this being 2. All right, a couple more sentences, 2 more lines, I think. Hopefully I won't run out of room. Since the limit as x goes to x naught of f prime over g prime of x exists, that's by the hypothesis here. This limit does exist. That means that both the sequence f prime of Cn over g prime of Cn and f of xn over g of xn as a sequence converge to the same limit. After all, term by term, these are exactly equal to each other. F prime of Cn over f over g prime of Cn is right here, and that's equal to f of xn over g of xn. Because this is differentiable, this limit converges. If this limit converges and this is equal to it, then it converges as well. So therefore, and since they converge to the same limit, we can simply say that the limit x goes to x naught of f over g of x is equal to the limit as x goes to x naught of f prime over g prime of x. And that's exactly what we needed to prove. And the Cauchy mean value theorem made this proof much more simple than it could have been.